Okay, I want to finish up this whole bonding chapter with a look at something that your book just totally ignores, but I really think you should at least be exposed to this a little bit, and that's hybridization of atomic orbitals. A hybrid in the animal world is when you take two unlike animals and crossbreed them. Like if you do a horse and a donkey, you get a mule, a hybrid animal. Orbital hybridization is if you take two unlike orbitals, say an S and a P, and mash them together. You can get an averaged orbital out of the deal, or what we call a hybrid orbital. Now, why would you do that? No good reason to. I mean, you're allowed to play with the wave functions, I guess, and average the math together, but what would make you even want to do that? Well, the reason you want to do it is because it actually ends up working. So it's kind of an ad hoc hypothesis here. We do it just because it works and not because we have a good idea why. But let's look at the example I give here, how quantum mechanics in the basic form with the electron configurations that we all know and love, how it fails us, and so how we have to adjust it. Let's take carbon, has an S2P2 configuration. Let's see here. Let me get to my drawing. Carbon's an S2P2, so right here's the nucleus. There's level 2s, and then there's 2py, 2px, and then the 2pz coming out at you. So let's put two electrons there in the s orbital. Then we'll say put an electron in this p orbital and an electron in this p orbital. Why? Because they're going to be split up because of Hund's rule. Now, clearly, these two electrons are already paired up, so they're not going to be bonding with anyone. The z orbital has no electrons in it at all, so I guess it's out of action. It's going to be an incomplete octet. This electron right here in this p orbital, well, it could pair up with another one. So let's bring another atom in here, let's say a hydrogen, overlap its electron cloud, and share to form a bond. So there's a hydrogen there. And we do the same thing with this one. So you bring a hydrogen in here, share its electron with carbon's electron, and form a bond. But you notice that's it now. Your carbon, I didn't say it, but it's right here in the middle over here. So that's your carbon. So based on what you know about SP configurations, S2P2 in this case, by all rights, carbon, when it bonds with hydrogen, should form the molecule CH2. And notice the bond angle in here. Well, that's on the y-axis. That's on the x-axis. So the bond angle should be a 90-degree angle in there. Okay? So if you buy into that whole S2P2 thing, what we have been learning since the third marking period, by all rights, when carbon bonds with hydrogen, it should form the molecule CH2 with a 90-degree bond angle and an incomplete octet. Not ideal, not optimal, but that's kind of where this leads us. Now, we know that doesn't happen. The real molecule that forms is methane, CH4. And when you do your VSEPR stuff on it, you find it's a tetrahedron, a very bad tetrahedron in this case, with carbon in the middle and the hydrogens bonded at each point of the tetrahedron. So bond to hydrogen, bond, and bond. So the real molecule is a tetrahedral shape and is CH4, not what we might have predicted just using the basic electron configuration. So clearly the atom is doing something beyond S2P2. So I made you learn all these electron configurations and how to do them for the elements. And now I'm going to give you the dirty little secret here. That only occurs when the atom is by itself. So if you have a carbon atom hanging out in space by itself without any other atoms nearby, yes, it's going to be an S2P2 configuration. But as soon as it comes near another atom and starts considering, hey, should I react with this guy? Its electron orbitals rearrange. The S's and the P's get mashed together and form some new hybrid orbitals so that it can end up in a tetrahedral geometry. Okay, why does it want to do that? I don't know, it does. I guess the main reason is because it increases the distance between the electron clouds and minimizes overall repulsion. But bottom line is, the atom has the electron configurations that we know and love only when it's by itself. When it's going to get involved in chemical bonding, which atoms usually do, it rearranges into some new hybrid configuration that you're going to have to learn how to deal with that. Okay, so why'd we bother learning the configurations in the beginning, like S2P2, if they're not even really there? Well, because that's the starting point. We won't be able to figure out how to get these hybrid orbitals if we don't have the S2P2 to start with. So you still got to know your electron configurations and your diagonal rule and all that stuff. But now the reason is because now it's just our starting point. Okay, so let me come back to the PowerPoint and we can continue from there. Okay, so we just discussed this. Basic quantum mechanics gets it wrong. The actual molecule has 4 hydrogens and a 109.5 degree bond angle, in other words, tetrahedron. So we need to form hybrid orbitals by merging the S's and the P's. Now, the rest of this is going to be looking at different possible hybrids that you could do. So here's the idea. Here's your S orbital. Here's your P orbitals. Okay? Now, they kind of color code them. Notice the S orbital has electrons paired up in it. This a 2s2. The p orbitals have one electron, no electrons. So the darker the shading, the more electrons there are in an orbital. If it's full, it's darkly shaded. If it's half full, it's partially shaded. If it's empty, it's not shaded at all. Whatever, there's just the color code they chose to use on this particular picture that I stole. Now, so here's carbon, S2, P2. When it's going to get ready to start bonding, what it will do is take the s orbital and all 3 p orbitals and merge them together, mix them up, and form 4, you put 4 orbitals in, an s and 3 different p's. So it's going to mash them together and form 4 new orbitals. That's important to realize. If you put 4 orbitals into it, you get 4 orbitals out of it. But notice these new orbitals are averaged. So we would literally take the mathematical function for a 2s orbital, the mathematical function for a 2px, 2py, and 2pz, add up all those wave functions, and divide by 4. And what we'll get is 4 new wave functions. And those 4 new wave functions are called sp3 hybrid orbitals. Okay? So a normal orbital is an s or a p or a d or an f. We call those atomic orbitals. We now get hybrid orbitals. Now, again, the orbitals are all called sp3 hybrids, which means there's an s and there's 3 p's thrown in there. It's rather unfortunate they put the 3 as a superscript because that looks like it should be 3 electrons, and that's not what it means here. It just means there's 3 p's in the hybrid. Okay? We're going to see other types of hybrids with different numbers of p orbitals mixed in there, so that's why they do that. So, in this first case, to explain methane, we mix the S and we mix all 3 P's together, and we get 4 new hybrids called sp3 hybrids. Now, notice you had 1, 2, 3, 4 electrons to work with. They're not going anywhere, but now you put those 4 electrons in the new hybrid orbitals. And there they are, following Hund's rule. Notice that gives us 4 unpaired orbitals, each one available to bond to a hydrogen. So now we do get CH4, 4 hydrogens to bond with. Even better, if you take those 4 hybrids and you draw the wave function, well, here's one of the hybrids. Now, they don't show it here, but it has a little tail on the other end. That's really not terribly important. But the hybrid orbital pokes up this way. The other hybrid pokes over this way. Third one back that way, fourth one out in front toward you. Notice those hybrids form a tetrahedron. Okay, so if you mash together your S's on all 3 P's, you get sp3 hybrid orbitals, and those hybrid orbitals automatically fall in a tetrahedral arrangement. And so they also automatically have 4 open bond spots. And so now we get hydrogens bonding onto each hybrid, forming a tetrahedral CH4 molecule, which agrees with what we observe in the real world. So Like it or not, apparently carbon atoms form sp3 hybrids when they're ready to react. Okay? Again, you wouldn't have expected this otherwise. If we had no way of measuring the bond angles and things like that, we probably would have lived our lives thinking, oh, it's just it bonds on the p orbitals, of course, obviously. But since we can measure bond angles and we know that they disagree with the 90-degree angles of p orbitals, we figure, playing around with the math, the orbitals must be doing this hybridization. Okay? So apparently that's what atoms do. They hybridize their orbitals and form sp3 hybrids to get a tetrahedron. Now, let's look at nitrogen doing the same thing. S2P3. So here's your S2, P1, 2, 3. Now, same idea here. If I want to form a molecule with nitrogen and hydrogen, I can mash together the S and all three P's and make sp3 hybrids, just like before. But notice now I have 1, 2, 3, 4, 5 electrons to fill in there. 1, 2, 3, 4, following Hund's rule, fifth one's got to pair up. So once again, I get 4 sp3 hybrids. Those hybrids are still arranged as a tetrahedron. One of them is a lone pair. The other 3 are available to bond, and so you get your ammonia molecule. Nitrogen in the middle, the tetrahedron arrangement around it. This one up here, this orbital up here, is the lone pair. The other 3 orbitals had open spots where they could bond onto hydrogen. And so you notice you get your trigonal pyramidal shape that we know that ammonia has. Okay, so you see how this hybridization theory perfectly explains the VSEPR shapes. Okay, the problem with it is you can't figure it ahead of time. Why did nitrogen do sp3 hybrids? Why didn't it do some other hybrid, like sp2 or some such? Don't know. It just, we have to go by the shape first. So you do your VSEPR, you find it's a trigonal pyramidal shape, or in the previous one we found it was a tetrahedral shape, and then kind of ex post facto, we go back and say, well, since it's that shape, it must have been sp3 hybrids. Other hybrids are going to correspond to different shapes. We want trigonal planar, there's a hybrid for that. We want linear, there's a hybrid for that. Okay? Right now we're looking at sp3 hybrids, and they're the ones that give us our tetrahedral overall geometry. Let's look at a water molecule. Oxygen, S2P4. So again, here's your S2, P1, 2, 3, 4. You had to pair up. Okay? Well, oxygen wants to get involved in bonding. It's going to mash its orbitals together. Create these sp3 hybrids again. You have 1, 2, 3, 4, 5, 6 electrons, so put them in. 1, 2, 3, 4. Go back and pair up. 5, 6. Okay? So once again, you got your tetrahedral sp3, but now lone pair, open for bonding, open for bonding. And so there's your water molecule, tetrahedral arrangement, lone pair, those are those two. The spot here open for bonding, this one we bonded a hydrogen on. This one over here is that spot we bonded a hydrogen on. Notice that gives us the tetrahedral angle 109.5, again tweaked a little bit because the lone pair is being extra repulsive. But you get your tetrahedral angle rather than a 90-degree angle like you otherwise would have predicted. So again, this perfectly agrees with what we know water molecules are like. So that's what orbital hybridization is all about. You take your S's and your P's and you mash them together in such a way as to get the shape that you want. Today we simply looked at what if it's a tetrahedral overall geometry. Again, remember that means a real tetrahedron or trigonal pyramidal or angular shape, depending on how many lone pairs you have. But if you have that tetrahedral overall geometry, that means your orbitals must have hybridized into sp3 configurations. If you have trigonal planar or linear or trigonal bipyramidal or octahedral or all those kind of things, there's going to be different hybrids for that. But we'll leave that as a future you problem and discuss that tomorrow.